The last talk is Pythia, improving data center utilization via precise contention prediction for multiple co-located workloads.
West Lafayette, Indiana. A place you've probably never heard of. It's where our university is, Purdue University. Definitely. All right. Welcome to this talk. As you can tell from the rainbow-like coloring that we have authors from various different organizations. I am from Purdue University. We have 4 different industrial partners involved in here. And by far the hardest job was to get the IP and the signatures from all of the different companies. Hardest part of getting this paper here. I'm going to talk about Pythia, and let's think about what the motivation for this is. So if you know of data centers, they cost a whole lot of money to build. They cost a whole lot of money to operate. However, the somewhat surprising thing when we started looking at this problem was that the resource utilization for these data centers tends to be very low. So if you look at the best managed data centers today, it tends to be of the order of 30 to 40% in terms of their utilization. So there is another trend which is happening, which would argue for increasing the utilization of the machines, which is that the machines are becoming resource rich, more resource rich. Think of the increasing amounts of memory that's going into each node. Think of the increasing number of cores that are going into each node. So these should argue in favor of your machines, your servers being more highly utilized. So what is the reason for the low utilization in the data centers? So it turns out the reason is that only a single application runs on one server. So why is that? So when you have so many different cores on one machine, why is it that only a single application, it may be a multi-threaded application, but why is only a single application running on one node? So digging in, the reason for that is paranoia. And what do I mean by that? It's the fear that the latency sensitive applications that you have, like search, like when you want to see your favorite cat video, or when you're a stockbroker and you are making a trade, those are extremely latency sensitive. And the fear of delaying any one of these latency sensitive applications is what causes this conservative choice that most data center operators make. Because latency, it has been found repeatedly, is money. A delay of half a second is going to lead to a significant fraction, 30% according to Google's numbers, leaving your search. So this fear is what causes them to compartmentalize and keep one node for one latency sensitive application. So there are various different kinds of resources that applications compete for. And if you look at the resources, they can be local resources or remote resources, local as in compute and memory, and remote as in network. So with today's hardware technology, it's relatively easy to partition compute cores, but it turns out it's very hard to partition memory, be it the capacity of the memory or the bandwidth to transfer data from one level of the memory to another level, like from L3 cache to L2 cache and so on. And it's hard to partition, compartmentalize the network. So in order to protect latency sensitive applications from potential contention on these dimensions, people take the conservative option. So there has been quite a bit of work in characterizing contention in cloud environments. So let us look at the prior art and 2 key observations that we make on this prior art. So the prior art tries to answer 2 questions. One question is, how much contention does one batch application cause? And if there is a latency sensitive application, how tolerant is it to contention which is caused to it by batch application? So I keep using the term latency sensitive and batch application. We already talked about what a latency sensitive application is. A batch application is one which runs for long periods of time, does not have strict time requirements. And typically, there are many of these batch applications which run in data centers. For example, I want to clean up my disks. I want to find out if there are certain disks with potential errors in them. I want to do regular maintenance kinds of operations or regular bookkeeping, accounting kinds of operations. So the key thing to keep in mind is batch applications have no strict time requirements. They have loose time requirements that this should finish in the next 2 hours and things like that. So looking at the prior art, what they try to do is for each batch application, they try to come up with what is called a contention score, which answers this first question: how much contention does a batch application create? So for specificity, we can look at this paper from Micro 2011, which characterizes batch applications by something called a bubble. So each batch application gets a contention score, bubble in this case, which characterizes how much contention it causes. And each latency sensitive application gets a sensitivity curve like this, which says for a given value of the bubble, what will be the degradation in the QoS of the latency sensitive application. So the QoS for an LS application is typically latency. So the first observation we make is that the contention effect is specific to the LS workload. You cannot use just a generic stand-in for the latency sensitive workload. So here we look at two different latency sensitive workloads. One is Redis, which is a key value store, and the other is MongoDB, which is a NoSQL database. So what we have on the y-axis is IPC, instructions per cycle, so lower is better. And what we have on the x-axis is the contention that is being caused on that particular node. So expectedly, as the contention increases, the instruction per cycle increase. However, the nature of the two curves are different. So what we find here on this is on the x-axis we have Redis, on the y-axis we have MongoDB. So if the same amount of contention causes the same effect on both the applications, you would expect all of the points to lie on the diagonal. However, we find that most of the points lie above the diagonal, which indicates that MongoDB suffers more from contention than Redis. So the takeaway from this is the latency sensitive workloads are different in terms of what kind of contention effect they suffer from. The second observation we make is that the contention effect changes with the degree of co-location. So there's lots of details in here, but let's abstract this out. So if you are running two batch workloads on a particular node, and to find out how much contention the two batch workloads will create, let's say we just sum up the contention from each of the batch workloads. Okay, so that's what we will get by the estimate. And this is what we actually observe by running it. So what you'll see here is that the estimate and the observed differ quite a bit. And the estimated one usually is higher than the observed one by quite a bit, by up to 76% in these combinations. What does this mean? This means that when we have multi-way co-locations, that means multiple batch workloads are running on the same node, then predicting the contention is quite challenging, and simply adding up the contentions from each of the batch workloads does not work very well. And the root cause behind this is that the batch workloads themselves are beating each other. So not only do the batch workloads cause contention against the latency sensitive workload, but they throttle each other as well. And therefore, just summing up gives you a higher value than what you observe in practice. And further, the error in this estimate increases with the degree of co-location. So these two observations help us come to our solution, which we call Pythia. So the key point of our solution is that it does workload-aware modeling of contention, and the goal is to increase the utilization, which further means that we want to be able to co-locate multiple batch applications on one node with the latency-sensitive application. So what Pythia does is it creates a model for multi-way co-locations, and it turns out that a relatively simple model, linear regression model, is good enough for this purpose. So the fact that a simple model is good enough means that the amount of training data that is needed to create this model is relatively sparse, which is a good thing. Now, Pythia can provide very accurate predictions for the contention due to multi-way co-locations, and this prediction is used during the initial placement decision. So a new application comes in, I'm trying to decide which node to place this on. With the current state of practice, you would spin up a new virtual machine on a new physical machine and put this new application in this new virtual machine. With Pythia, what you can do is you can find out what is going to be the contention caused by the multi-way co-location, and then you may be able to put the application on an existing physical machine. Now, this initial estimate may still be erroneous from time to time. Maybe your latency sensitive application's load changes. So just that initial decision may not be good throughout the existence of your latency sensitive application. And therefore, Pythia also incorporates dynamic monitoring and control schemes, whereby if the LS workload suddenly becomes very demanding, then Pythia would also throttle any of the batch workloads by reducing its priority. And hopefully this kind of throttling will happen infrequently if we do a good job, and it turns out empirically we do, of this first step of doing this estimation. So here's a high-level workflow. Pythia involves a bunch of offline steps. All the heavy-duty stages are offline. So it does an offline profiling of the sensitivity and contention of the latency sensitive and batch workloads. Then it prunes and samples this overall combination space. What this means is if executing one latency sensitive workload with one batch workload already creates too much contention, let's not even think about multi-way co-location. And then it does opportunistic data collection for multiple co-locations. What this means is the cluster, the data center cluster on which we are running this, whenever there is some idle time, you can go ahead, run some experimental runs to create the training data. Then it creates this regression model, trains this regression model and comes up with the coefficients. And during the online phase, it finds the proper co-location when a new workload comes in and then schedules it on the virtual machines running on these different physical machines. And whenever there is a slack time, you can opportunistically go and collect more training data. So sort of on the lines of online learning, you can keep updating your models, but you don't need a big heavy-duty offline phase for doing that. So here's just a little bit of math, and I'll try to abstract out what the key point is. So the mutual contention which is created by a set of batch workloads is given by the simple linear regression model. And what BWI is that's the contention score from running one particular batch workload, WI, and CWI is the coefficient for that. So in this prior art, this would simply be an addition. In this case, we are able to learn the coefficient CWI. By solving a least square optimization problem. So the weights CWI represent the tendency for that batch workload WI to suffer interference. So if CWI is high, that means that batch workload WI is relatively resistant to interference, which means that when it is run with an LS workload, it will cause higher amount of cache and memory pressure. So if we look at the evaluation for Pythia, this is about 5.5 kloc, and the LS and the batch workloads are run on different cores. We never shared the same core. For the LS applications, we use Redis and MongoDB as we discussed earlier, and we use a fairly large variety of representative batch applications. 19 of the 26 are found to be co-locatable from Parsec and Spec benchmarks. And we run this on a fairly large production cluster at one of our industrial partners. Each node has 16 cores divided into 2 sockets and a fairly generous amount of memory. We use 2 cores per workload, which means we have a maximum degree of co-location that's possible is 3. So 3 batch workloads plus 1 LS workload, because we reserve 1 socket for the experimental monitoring purposes. So we have 1 socket that's being used. So the first experiment shows how good Pythia is in terms of predicting the contention that's going to be created. So the metric here used here is IPC, instructions per cycle. IPC is considered to be a good stand-in metric for latency. Latency is what we really care about. But when you do experimental evaluation like this, latency turns out to be a fairly noisy metric. So IPC is used as a good stand-in. So instructions per cycle, lower is better. And the takeaway is that most of the points lie around the diagonal, which means that the actual IPC that is seen with the co-location is close to the predicted IPC. And this we do only with 5% sampling rate over the entire search space, which boils down to us using a relatively simple model, which means that sparse amounts of training data is sufficient. The second one is looking at the dynamic throttling of the batch workloads. So what we have is Redis running once without PIPO. PIPO is our dynamic mechanism, and then here running with the dynamic mechanism. So when the load becomes high, then the Redis QoS drops below the threshold, the 95% threshold. But with the dynamic throttling, it can stay continuously above the 95% threshold. This one is looking at the improvement in the cluster utilization. So the metric here is the number of cores that are being occupied by jobs divided by the total number of cores that we have in the cluster. And there are three protocols being compared. One is Pythia, the other is the state of the art, which was bubble up, and this one is the multi-bubble up, which is an extension whereby you simply add up the contention scores from each of the batch workloads. So what we find here is that the cluster utilization that you can get is quite a bit higher if you have some slack in your QoS budget. If your QoS budget is 99%, which means you can afford only a 1% degradation in the latency, then it doesn't really matter which one you use. But if you have a larger slack in your QoS budget, say 80%, then you find that Pythia, even 90%, Pythia is able to utilize your cluster almost fully. And that cluster utilization now translates into a reduction in the number of active machines that you have in your cluster. So here the lower number of active machines is better because then you can power cycle your other machines, thereby saving on energy and operational costs. So what we find is that the number of servers that are used if you're using Pythia versus the extension of the prior work multi-bubble up, the blue bars, Pythia bars, are quite small, especially as your QoS policy becomes more tolerant. So with an 80% QoS policy, the number of active machines that you need to power up is reduced by 44% with Pythia. So that's it in terms of the evaluations. Let me conclude by drawing some insights from this work. So the first insight, the observation is that in order to increase the utilization of data centers, it is very important to do multi-way co-location, so multiple batch workloads. And simple additive prediction of contention is not good enough. The second observation experimentally that we make is that the impact of contention on different LS workloads can be very, very different. So then our solution, what it tries to do is accurately predict what will be the contention from multiple batch workloads. And then after this initial estimate, it uses a dynamic throttling mechanism for the batch workloads if it is needed. So the end result is that it can significantly improve the cluster utilization. The drawback of our work is that if you throw a completely unseen application at it, then it cannot work very well in practice because it hasn't gone through this profiling phase for that unseen one. However, there is some prior work, for example, Paragon from Stanford, which uses something like SVD in order to characterize unseen workloads. So this could be used in combination with something like that. That's it. Happy to take any comments or questions.
So thank you, Saurabh. We have one question here in front.
Thank you. So is contention network contention or memory contention, or so how is the contention score calculated?
So in general, in this kind of work, contention can be any one of the pieces of contention where the current hardware mechanism is not very good in partitioning. So this could be local memory or I/O, or it could be remote I/O or remote network. So in our experimental evaluation, we look at the contention for the memory, but the broader scope of the work is broader than that.
Thank you for the talk. Two questions. First, you mentioned that you sampled the co-location combination space, and then you find the proper co-location. And contention by itself, if you run one application on a single machine, no contention can happen. It's obvious. But if you run multiple, then there's a risk of contention. Assuming that we have how many application types? 100, 1,000, 100,000?
Yeah,
What is the complexity of that combinatorial problem? And is it computationally feasible?
So in the data centers that our industrial partners talk about, it's of the order of somewhere between 100 to 1,000 different applications that will be running.
Sorry, one more time.
Between 100 and 1,000 different kinds of applications.
True, but then how computationally feasible would this method be? Because you should consider all the different app workloads combination with each other and then find the right combination.
Right. So one important effect that we see here is that the coefficient for a batch workload, how much contention it will create, depends only on the degree of co-location, not on the specific other batch workloads which are running. So then you could calculate the coefficient for a degree of co-location 2, degree of co-location 3, degree of co-location 4, and we don't have to run into that combinatorial complexity.
True. Just a follow-up on that. The reason for co-location, if I understand correctly, or the reason for not co-locating is the sensitivity of the latency-sensitive applications.
Exactly.
So the one that we care are the latency-sensitive applications.
Exactly.
So shouldn't we care about them? So if you put 5 batch workloads, the latency of them would not matter.
That's right.
The impact of those batch workloads on the latency-sensitive one is the one that matters. Mm-hmm. But how do you count that in? Yeah,
so all of our experiments look at the impact on Redis and MongoDB, which are examples of latency-sensitive workloads. So you're exactly right that what the latency of the batch workloads does not matter in small time granularities. But all of our work and our evaluation is looking at the latency of the latency-sensitive applications, which are Redis and MongoDB in our evaluation.
Thank you.
What are the percentages? Clearly, your benefit depends on how much the leeway for QoS is. You show 20 to 10. What is the typical?
Yeah, so this actually covers the range of QoS degradation that today's data center providers seem happy to live with. Some applications have very little slack, so 99%, and some other latency-sensitive applications you're willing to put up with up to a 20% increase in that latency. So this range, 80 to 99%, I believe captures the practical impact quite well.
Okay, let's thank Saurabh.